In this video, we're going to take a look at how the pH of a salt, or what the pH of a salt from a weak acid strong base will be. So the same steps will be followed for the first few steps. And essentially after that, there's a couple extra steps that are different from the previous example, but it's all the same thing. So here we have a salt, and we want to know what the pH of this salt's going to be for that concentration. So as we typically see, we need to dissolve the salt in water. We need to do a dissociation to see which ions will form. And so we'll get the Na plus, AQ, plus the NO2 minus, AQ. And so now we need to test out the salts by hydrolysis to see what their effect on pH will be. I will also write out the concentration of the salt over here. We'll need that for later. Let's test out the Na plus first because we've done that one before. So by experience, it should be pretty straightforward. We're going to put Na plus in water, and it could undergo hydrolysis, maybe. Let's see. If it does, the Na plus will go with the OH because the OH is minus and the Na plus is positive, and then that'll result in some H plus forming. So technically the Na plus would be acting as an acid because it's forming some H plus. But notice this is a strong base. So this direction will not happen. It would rather stay as Na plus. So this is the salt of a strong base, no effect on pH. So we don't need to worry about this one too much. But let's go take a look at the other one, this NO2 minus. I'm going to do a hydrolysis reaction for it. So NO2 minus AQ plus some water. The NO2 is minus, so it'll connect with an H plus. So we'll get HNO2. When you put H plus and minus together, there's no more charge. Aqueous plus, so the H came from the water, there's OH minus here. So I don't recognize this acid as being a strong acid from our list of acids we had to memorize, but let me go double check from our table here. HNO2 would be nitrous acid. And it doesn't have a large Ka. It doesn't have a very large Ka. So because it doesn't have one of these very large Kas here, nitrous acid is a weak acid. So what does that mean? Well, this is a weak acid. So this is the salt of a weak acid. And it's acting as a base because it's producing OH minus. So acts as a base. And so this does happen in an equilibrium. And this is a part of the salt, the NO2 minus, that's going to be affecting our pH. So if it's acting as a base, a weak base, chances are our pH is probably going to be higher than 7. Let's see if that's true. So we'll create an ice table. We need the initial concentration of NO2 minus, and we can get that using our mole ratios here. So all this would become 0.10 molar since it's a 1-to-1 ratio. So 0.10 molar there. We don't care about the water since it's a liquid and its concentration is not going to change. This would be 0 at the start, so with this would be minus x. This would be plus x and plus x. This would be x and x. And this is 0.10 minus x. Our goal is to find the pH, but based on this ice table, we can't find concentration of H2O plus. We'll have to find concentration of OH minus, and then from there convert to pH in one of the methods that you're comfortable with. So what's important to understand here as well is that you can't make a Ka expression from what you have here because this is a base. So what you're making is a Kb expression. Kb is the concentration of OH minus times the concentration of HNO2 over the concentration of NO2 minus. And if we replace all those x's there, that's x times x over 0.10 minus x, which is x squared over 0.10 minus x. Now we have to go look for the Kb of this thing over here. Because that's acting as a base. So if we go to our base table, I don't see it. It's not there. But remember we learned a relationship at the start of this video series that if you have the Ka of the conjugate acid, 5.6 times 10 to the negative 4, you could find the Kb. So remember that Ka times Kb is equal to Kw. Therefore, Kb is Kw over Ka. So Kb will be Kw over Ka, so 1.0 times 10 to the power of negative 14 divided by 5.6 times 10 to the power of negative 10. Is that what we said, or was it negative 4? I forgot already. Let me go back and check. 4. That's right. Sorry about that. And so we get the Kb is, so 10 to the negative 14 divided by 5.6 times 10 to the power of negative 4. 1.7857. I keep all my digits in the calculator, times 10 to the power of negative 11. So now we can plug that Kb into our Kb expression. So it's just an extra step to find Kb because we're dealing with the base, not the acid, and the Kb was not included in the table, but we did have the Ka of the conjugate acid, so we could use our Kw is equal to Ka times Kb relationship to find the Kb. So remember that Kb is x squared over 0.10 minus x. Now that we have Kb, we can say that Kb is going to be 1.7857 times 10 to the power of negative 11 is equal to x squared over 0.10 minus x. Now before I continue solving for x, I'm going to try the 100 rule so I can avoid doing quadratic formulas with all these complex numbers. So my initial concentration was 0.10 from the ice table over the Kb, not the Ka because we're using Kb. And when you do that, you'll see that you get over 100. Therefore, you can simplify. So let's continue here. So 1.7857 times 10 to the power of negative 11 is equal to x squared over 0.10. So that means that our x squared is equal to 1.7857 times 10 to the power of negative 11 times 0.10. That means that our x is simply the square root of that. So x is square root of 1.7857 times 10 to the power of negative 11 times 0.10. And this is also the concentration of the hydroxide, which is what we want in our table. So times 0.1, square root of that, we get 1.336, and there's more digits, times 10 to the power of negative 6 molar for the hydroxide. Now remember, the question is asking us for the pH. So we can't find the pH right now, but we can find the pOH. And then from there, we can find the pH. Or you could also do the Kw is equal to H plus times OH minus, solve for H plus, and do the pH from there. But we'll just find the pOH. So pOH is negative log of the concentration of OH minus, which is a negative log of the 1.336 times 10 to the power of negative 6. So we get about 5.874. We know that the pH plus pOH is equal to 14. Therefore, the pH is equal to 14 minus the pOH, which is 14 minus the 5.874, which is equal to 8.1259, so on and so forth. We want 2 sig figs, so therefore pH is approximately 8.1. And this makes sense because we have a salt of a weak acid, which acts as a base. So when you have the salt of a weak acid, it is going to act as a base. Therefore, the pH will be higher than 7. So when you have the case of a salt, where part of it comes from a strong base, that part won't affect the pH. But the part that comes from a weak acid, that part will affect the pH as a weak base. And therefore, you'd expect your pH to be above 7 in that scenario. So in the next video, we're going to take a look just briefly at what happens if your salt is derived from weak acid and weak base. What do we do in that situation? Because both of them would be affecting your pH, theoretically speaking. We're going to simplify it a bit by just doing more of a qualitative, rough estimate of where the pH is, but we'll take a look at it anyway so you can get some idea as to how to approach it.